Find the open intervals where the function f of x is equal to 18x minus 18 times e to the negative x is concave upward or concave downward. Find any inflection points. All right. So this is a very weird function. We do not really know immediately what the graph of such function looks like. But we have our methods to find out where it is concave upward and concave downward. As a quick reminder, the best way to remember how the derivatives are interlinked with the concavity, the behavior of the graph, I like to always make myself a little sketch of three different functions. I'm starting with a cubic one. This is the graph of a cubic function. Let's say this is the original function f. Now, the derivative of this function has to be a quadratic and it has to be zeros right here where my original function had minimums and maxima. So in other words, a first derivative could look like this. It would be the graph of a quadratic. Now the derivative of this one, of the blue one, of the first derivative, is our second derivative. And this is just the graph of a linear function going through 0, where the first derivative has a horizontal tangent line. Now, these three graphs are basically showing me everything that I need to know about my second derivative test. I am looking at my second derivative, the graph of it, where this graph is 0. I have a possible inflection point. An inflection point is a point where my original graph changes the concavity. It kind of wiggles around. So, now, where my second derivative is negative, that would be right here, my original graph looked like what? It was concave downwards. And where my second derivative was positive, the original graph was concave upward. So, concave downward, concave upward, concave down when my second derivative is negative, concave up where my second derivative is positive. And this is what we're going to use now. So in other words, the first thing that we're going to have to find is the first derivative. First, find the first derivative of f. Let's have a look. This is the sum of two functions. The derivative of 18x squared is 18. The derivative of negative 18 times e to the negative x, I will have to use the chain rule, which says it's going to be negative 18 times e to the negative x multiplied by the derivative of negative x, which is negative 1. So in other words, I have 18 plus 18 times e to the negative x. Now I'm going to have to find the second derivative, which is nothing else but the derivative of the derivative. Looking at 18 plus 18 times e to the negative x, I will end up with 18 times e to the negative x multiplied by negative 1 again is negative 18 times e to the negative x. The derivative of 18 is, of course, 0. Now, in order to look at this a little bit better, I'm going to rewrite this function in the following way, with a positive exponent. Negative 18 divided by e to the x. Now, where this second derivative would be either 0 or undefined, I would have found possible inflection points. But when I'm looking at e to the negative x inside my denominator, this function is, first of all, never going to be equal to 0 and always going to be positive. This is going to be always positive. Positive. The graph of e to the x, just a quick reminder, looks like this. It is the graph of an exponential function. So that means that there are no inflection points. In other words, my graph will not change its concavity. And as a consequence, all I need to find out is now, what kind of a concavity do we have? I will plug in one value into my derivative, my second derivative, to find out whether it's positive or negative. A moment, let's make clear that the denominator is always positive. So since the denominator is always positive, the overall expression is, of course, going to be always negative. And since my expression, my second derivative, is always negative, I will have a scenario that looks like this. Because my second derivative is everywhere negative. No inflection points. Concave down. On the open interval from negative infinity to positive infinity, everywhere where my original function was defined. Now, before we are leaving this problem, let's just quickly look at the graph of this function. And we are noticing I had to change a little bit the labeling of my x and my y-axis in order to display what the graph actually looks like. And it really looks like that it is concave downward everywhere over its domain.